Ryan and Desalytics for giving us the opportunity. So my name is Alvaro Lagartos. I'm the application engineer for LG Water Solutions for Europe, Africa, and Latin America. So I know you've been all talking about all different points when it comes to the pretreatment. I'm going to jump a bit further into the RO process itself. My presentation is about reducing the RO system OPEX through the RO membrane optimization. What I mean here with optimization, I will be focusing on one particular part of the RO membrane, which is the feed spacer. Okay, this particular component of the membrane models has a huge impact when it comes to the energy and chemical consumption, chemical waste, and therefore is strongly linked to the operation cost of your RO process. So thinking of the two of the main issues we have in our operation, now we have fouling, which obviously is the deposition of different particles. We've been talking about different treatments to try to remove all those particles now, but we have they could be organic, inorganic, biological. The point of these particles is that they get stuck to membrane surface, mainly the feed spacer within the membrane models. And this happens because there are different regions when the feed flow is crossing the membranes that they will have low velocities, and therefore they are able to settle down and start growing inside the membrane models. As a consequence, we know they reduce the flux, increase the drop pressure across the membrane. And in addition, we also have what is called concentration polarization, which is, as you might know, it's a common thing for membrane processes, which is the high concentration of solutes on the boundary layer next to the membrane or the active membrane of the active layer of the membrane. As a consequence, we usually have high osmotic pressure, which can lead to reduce the flow crossing to the permeate side and also increase the salt passage. Okay, those are two of the main issues, and both of them, they are very really influenced by that particular part of the RO membrane, which is the feed spacer. What is the main purpose of the feed spacer in an RO membrane model? It's besides being a mechanical, the mechanical separation of the different layers of a membrane, is to enhance the mass transfer. So the first purpose is to enhance the mass transfer to minimize the concentration polarization. So we want to minimize that particular layer so it could be as thin as possible. On the other side, it's also responsible for the pressure drop across the membrane and also for the fouling potential, because at the end, the feed spacer is what the feed flow is encountering when it's crossing the membrane. And also fouling potential, because it's also going to define those particular areas where I say you're going to have low velocity, the stagnant areas. How could we optimize the design of the feed spacer? Well, there are different parameters. What is important is normally those actions that are going to be good in terms of reducing concentration polarization, they might play the other way around when it comes to pressure drop or fouling. And vice versa. So it's important to evaluate all of them to identify which ones are the more critical ones and how we could combine some balance to get the more optimal design. Among those parameters, probably the main ones, besides obviously the thickness, which is very linked to standards in the industry, at least these days. We have the hydrodynamic angle, which is the angle formed by two filaments, and is the angle that they are pretty much facing against the feed flow. Also, the geometry is very critical. Now, those filaments, those strands, the cross section, the torsion, thickness, porosity. So all those parameters, they are the ones we have to play around in order to achieve the most suitable design. Well, in LG, a couple of years ago, we developed a new feed spacer. It's called LDP. And that's not new. I mean, most of the membrane manufacturers, they've been working, obviously, focusing on the feed spacer because they realize it's a very critical part, to further optimize the RO membranes. So our objective was to reduce the DP, but maintaining the concentration polarization to the level that we already had with our standard. The way we did that was you have thickness, diameter. I already said this is quite standard in the industry. Now, thickness is related to the diameters, which are pretty standard in the industry. And until today, it seems that it's very complex in order there's no room, available room, no, to fit any thicker spacer. So we went to focus on the geometry. There in that picture here, you can see the difference between our standard previous and the LDP feeder spacer. And we managed to achieve a membrane that it was maintaining very similar concentration polarization and reduce the DP significantly. The actions that we implemented was first, we reduced what is called the SPI. SPI stands for strand per linear inch, which it gives you an idea of the kind of the density of that feeder spacer. And it's quite logical. Now, if you reduce the density, then you reduce the resistance that the feed flow is gonna face while it's crossing the membrane. Then we have we address the strand design and mesh. This is changes in the thickness, the torsion, and the porosity of the strands. The idea here was to find other solutions that will help to reduce the concentration polarization, and we could compensate the other measurements that we were implementing, not the other modifications that we were implementing. And finally, we reduced the hydrodynamic angle. You can see from the picture, it's quite obvious. Obviously, if you reduce this angle, straightforward, you get a great reduction in drop pressure. Obviously, the resistance will be lower to the feed flow. And also, you reduce the stagnant areas. Why is this? You reduce the falling rate because you increase the cross-flow velocity. If you reduce the cross-flow velocity, then it will be harder for particles to start settling down on the feeder spacer or membrane surface. And of course, this is not only applied to normal operation, but it's also applied when you are performing CIPs. So you can improve the efficiency of your CIPs. No? All these changes, we managed to get a drop in the drop pressure between 30–40%, which is quite significant if you think about it in brackish water system with several stages. But also, as I say, it helps to reduce the falling rate, and that will lead to reduce the number of CIPs. So what I want to show you next is our experience that we have applying these modifications with the LDP feeder spacer for a pilot trial that we have on this site. It was a steel industry site where they were recycling. There was an industrial wastewater recycling plant to order to keep reusing that water as part of the process. So in order to be qualified to become a vendor, you need to pilot for at least 6 months, and they have different trains. So they install our membranes in one of the trains, and outside they install also another membrane from one of our main competitors, a similar kind of membrane with low differential pressure technology in that model. The membrane that we had installed was the LDPW 400R Generation 2, which is a membrane we have with the highest rejection in our brackish water portfolio, and incorporates the low differential, the LDP feeder spacer. The system, as you can see, you were talking about the treatment. We had that particular plant, the water was kind of complex, okay, kind of between medium and high fouling potential, let's say. I had quite comprehensive, as you can see, pretreatment for some filtration UF before hitting the RO system. And the results we got from this plan, we were running there for almost 8 months. And this is the normalized permeate flow. You can see how our membrane was showing a higher normalized permeate flow compared to our competitor, besides the fact that they have similar specs in terms of permeability. That means obviously in energy consumption, our membrane could provide certain advantage. But the critical thing here was the number of CIPs. The arrows that you can see at the bottom of the graph, those are the number of CIPs that each manufacturer, each train with different membranes had to perform. You can see while on the same time we performed 2 CIPs, the competitor had to perform 5. So as I was saying before, the feeder spacer has a huge influence in the fouling rate. Therefore, if you are able to reduce that fouling rate, then you are able to space longer the CIPs required, which at the end is translating reducing the chemical consumption, and also you are increasing the durability of your membrane. So all those little things just by minor modification, optimization in your feed spacer. As a consequence, this graph shows the normalized salt passage. You can see how our membrane during the whole trial was very stable in terms of the normalized salt passage that it was delivering. You can see how the competitor's membrane was struggling at the end, and the salt passage was increasing exponentially. As I said, remember what I said in the slide before, the number of CIPs. So among the possibly reasons why the other membrane was performing like this, obviously one could be that due to the higher frequency of CIP, the membrane degradation is more significant. At the end, if you want to maintain your RO membranes, what you have to do is to extend the time between CIPs, no? Because once you the more you expose the membranes to different CIPs, the degradation keeps increasing, no? And then the durability drops. And finally, the normalized differential pressure. You can see from here what I was saying before, the LDP feed spacer, due to those changes, particularly, the hydrodynamic angle, as I was saying, is reducing the delta P significantly. At the start or the first few weeks of operation, we can say how there was a difference between the two different elements, our membrane and the competitors, nearly 40%. But also you could see how was the trend in terms of fouling rate. So that's one of the other advantages, no? So as you can see, a feed spacer plays a real key role in the membrane operating cost. Is strongly linked to the energy consumption, because it's what is facing the feed, and differential pressure, obviously the higher this differential pressure is, the higher will be the feed pressure. And think about in a brackish water system, as I say, in a seawater system, these advantages, it's true that, it's not so significant because the differential pressure in a seawater system represents a small amount compared to the full system. But in the brackish water system, even if you just use a couple of stages, easily you can get close to 10% or even something between 10 or 20% savings just by improving and optimizing that particular part of your membranes. You see also what I said, the influence is not only the DP, but also reducing the fouling rate, improve the cross flow velocity, reduce the stagnant areas, and that will reduce the number of CIPs required, the chemical consumption, and at the end, obviously, the membrane durability. So you see, for instance, we have this LDP spacer in different models. This is one of them, LGBW400RG2. And you can see, for application like this one with industrial wastewater, and as I say, a complex water with medium to high fouling potential, that it was delivering quite a stable and successful performance. So the idea here is always, small changes still, is the way to go to keep optimizing the RO membranes, no? Or the RO process, or the desalination process itself, whether it comes from the treatment, as you were guys all addressing before, or even if it comes, to the RO system itself. So the objective at the end is always maximize, obviously, the plant uptime, no? And obviously make RO processes or desalination more sustainable in the future. Anyway, thank you for your time, and that was all from my side.
Thank you, Alvaro. Excellent presentation. We've got a few questions from Jochen. I'll keep one of them. What was the main fouling of the membrane in the steel manufacturing project?
The main fouling that we have in this system, they were coming from organics, I believe, and also certain inorganics, but I don't have the details from the autopsies.
Okay, and a quick one, is the new LDP improving the concentration polarization effect?
It's maintaining a similar concentration polarization as before. Therefore, it's not improving, it's maintaining the one it was before, that it was already successful. At the end, when you want to keep it to a low level, that it doesn't affect the operation of your RO system.
Okay, thank you, Alvaro.